Today we're going to be talking about vectors. So a vector is a mathematical quantity which has a magnitude, right? And magnitude is just another word for size. So it has a size and it has a direction. So vectors are something which have magnitude and direction, right? And the opposite to a vector, you could say, is a scalar, right? A scalar just has a magnitude or a size. Okay, so let's illustrate this with an example. So let's say you are a famous soccer player, Leonardo Messi, and this is your soccer ball. You're Leonardo, and you've got a soccer ball, and you kick it in that direction, right? Okay, and it stops about here, and it's sad because you kicked it. Okay, so if I told you that this ball has traveled 20 meters, right, and that's all that I told you, then that is a scalar quantity, right? Because I've only told you the size of the distance that it traveled, right? So it traveled 20 meters. There's no direction associated with this. So I'll just write that down. And I'll do it in red because I wrote scalar in red. So the distance is 20 meters, and that's a scalar quantity, right? And what would be the vector equivalent? Well, if I told you that the ball traveled 20 meters to the right, that's a vector. It's a vector because it has direction associated with it. And there's many ways to indicate direction, right? I've sort of used a qualitative description here, but you could be more quantitative. You could say it's moved perhaps at a 45-degree angle, or you could say it's moved northwest, you know? So there's many ways of expressing direction. And because I've included, so the name that we gave this quantity is called distance, and this also has a name. This is called the displacement, right? Displacement is basically how far away the final position is from the starting position, including direction, right? So displacement, ooh, just out of space there. Okay, displacement. So 20 meters to the right, and because I've included this direction, it's a vector. Okay. What are some other examples? Well, you have force. Force is a vector, right? Because you can apply a force in a particular direction. You have velocity, which is how fast you're going and what direction you're traveling in. Velocity. Magnetic field, right? So the Earth's magnetic field is a vector because it also has a strength and a direction associated with it. Okay, what about scalars? Well, I'm just thinking off the top of my head here, but temperature is a scalar because it does not have a direction, right? You don't say it's 20 degrees left. You have, what else? Length. Well, we've just been through an example of length. Height. Time is a scalar, right? Unfortunately, we can't say we're going 2 seconds back because time only goes forwards. It's a scalar. Okay. How do we represent vectors? Well, often vectors, as I've done here, they're sort of drawn as arrows, right? So let's draw one. Let's say you've got this vector here, right? And they're drawn as arrows. And in terms of labeling, so there's a couple of things that you'll see, right? And I'll write them over here. So notation. So in textbooks, what you see is sort of like a bold letter. So just like you can when you're dealing with normal algebra and you're writing down a variable, you can name it whatever you want, right? For example, let x equal length. So here I'm just calling this vector A. So in textbooks, what you'll see is a bold letter, right? So this is textbooks. But when we're writing stuff down, it's really tedious to make all our letters bold, and it's a bit time consuming. So to save time and to make it less ambiguous, see, because what's the difference between here and here, right? It's a matter of it's subjective whether it's bold or not. It's hard to tell which one's bold unless there's a clear difference. So when we're writing it down, we use this symbol here, which is called a tilde, right? Think of waltzing Matilda. So we use this to represent a vector, just to tell whoever's reading our work that we're talking about vectors. So in this case, I'm going to label this A. It's a slightly different shade of blue. Okay, and there's one more way we can represent it, which is by specifying the starting point and the ending point. So for example, let's call this A, and we can call this B. In that case, we would say that this is the vector AB. Yeah? Okay. So that's how you would... So those are the different notations that you can use when you're specifying vectors. So this is the graphical representation of a vector, and if we sort of superimpose a set of axes, my lines will probably not be the straightest, but that's okay. I think that's good enough. That's the x-axis, that's a y-axis. So you can see that each vector will have an x component and a y component. But instead of calling them x and y components, we call them I components and j components. So I'm just going to write that down here. So vectors have I components, right? So the I component basically just tells you how far it goes in the horizontal direction. They have an I component and they have a j component. Okay. So you'll notice that I wrote the little tilde below the i's and j's. So because these have definitions, right? So whoops, I meant to change color there because it's looking a bit too white for my liking. So there you go, there's a bit of yellow. So the I vector is a vector of length 1 in the x direction. Yeah, and when I say in the x direction, I mean in the positive direction of the x-axis. So this is I, right? And that length there is 1. Yeah. I'll just label a few more. Let's say that goes up to 4. Okay, so because our vector goes up to 4 on the x-axis, we need a few more i's to make up our vector, right? So we're going to need 4 in total. So there's 4 I vectors here. So in other words, you could say that the horizontal component of our vector is 4i, right? And the j component, the definition is, you know, pretty much the same, except it's in the y direction, right? So it's a vector of length 1 in the y direction, or in the up direction. Oops, in the y direction. So it's a vector of length 1 pointing up. Right, so let's say this was, maybe this goes up to 3 here. And that would be 2, that would be 1. And okay, so that is j, right? So to make up our vector, which is the blue vector, we need 3 of these j vectors, right? There we go. So this in total becomes 3j. So maybe I can, this will get a little bit messy, but I will sort of draw this green line above all of these. And that is 4i, right? And this whole thing here, this pink line becomes 3j. So yeah, 3j. I'll just write that a bit clearer. So in other words, we can say that A is equal to 4i plus 3j. So I have a bit more to say, but I'm going to move down a little bit because we're running out of space. So in fact, I'll just rewrite this here. So A is 4i. So whenever you're dealing with vectors, you're usually going to be given, you know, what the algebraic components are. Or you might be given the 2 points. So you might be given the coordinates of A and the coordinates of B. Okay, but what I wanted to mention was that there's another notation that is sometimes used. Instead of writing it as 4i plus 3j, sometimes you will also see it like that, 4, 3. This is in matrix form, right? It can sometimes always also be with square brackets, that doesn't matter. 4, 3. So this is basically means, so this is a column with 2 rows, and the first row is just the I value and the second row is the j value. so it's the j component and the I component. So yeah, that is another way of saying the same thing.